Lecture 8b, two examples of vertical plates. Now let's do another example for a trapezoidal plate. Okay, and this will be a dam. Let's say we want to compute the force on a dam with a water level of 700 feet. At the 700-foot level, the dam is 1,000 feet wide. So it's 1,000 feet wide right here. At the base of the dam is 500. So here's my sketch. Here's the dam looking like a trapezoid. The top is 1,000 feet. The bottom is 500 feet. Okay, and now I'm going to assume the water level is right here at the 700-foot mark. But here's my y-axis, and as usual, I put y equals 0 at the bottom of the object, in this case at the bottom of the dam. Then the depth of the water, say at this point, this is some arbitrary value y, is 700 minus y. You can verify that a little bit if you want, because when, say, y equals 700, d equals 0, there is no water right here. You're right at the surface. When y equals 700, when y equals 0, then d equals 700, because you'd be down here at the bottom, which is under 700 feet of water. So this is the depth of the water, which I need for my pressure calculation. Remember, pressure is going to be gamma times depth. And now I need to know the width. The width was not constant as it was in case of the box. Here it's going to vary. It's going to vary from 500 to 1,000. So I've written this as 500. It's a linear variation. 500 over 700 times y. When y equals 0, it's 500. When y equals 700, it's 1,000. I need the width because I have to calculate the area. All right. And the area is going to be width times dy. dy is going to be each little section. I divide this vertical plate up into little sections. Okay, so here's my calculation. Again, first I need pressure. And pressure is gamma times d. So gamma, which is specific weight of the fluid. And here's the depth, 700 minus y. The fluid changes as you go down this vertical plate. Now the width of the dam is a function of y. I'm going to write that as width as a function of y. I wrote that here just like I did on the sketch before. Okay. Now, force equals pressure times area. But when I'm integrating for a vertical plate, it's going to be the pressure at some depth y times the width of the plate at y dy, going from the bottom of the object up to the top. Okay, usually 0 to some height, which I'll call h. Right. In this case, we're going from y equals 0 to 700. That's the whole height of the dam. Gamma is the specific weight of whatever the fluid is in the dam, probably water, times the depth. I'll get the pin here a minute. So here's your specific weight. This is the depth of water, and this is the width as a function of y. Easy to integrate. And that's the force acting on that whole face of the dam. Now let's do the circular end plate. This is a little bit harder. Okay, we want the force acting on the end plate of a 3-foot radius drum under 10 feet of water. So here's the end plate of the drum. Again, I don't care about the sides of the drum at all, only the end plate. And I'm looking at the forces that are acting on this end plate. This is my sketch. Again, here's my y-axis. It's lying under 10 feet of water at a 3-foot radius. So 0 is the bottom of the drum. 6 is the top of the drum. This is under 10 feet of water, so 16 is the top of the water. The distance, the depth of the water, is not 700. It's going to be 16 minus y. So at the bottom is under 16 feet of water. The top of the drum right here is under 10 feet of water. The width is what's going to be the problem. Here's the pressure. The pressure is gamma d, specific weight times depth, which is specific weight times 16 minus y. All right, that's easy to do. Now to get the area, which I'll need for the force calculation, I need to find the width as a function of y. Right. By symmetry, I can say it's 2 times x of y. Let me show you what x is from looking at the previous slide. Okay, so I need the width of this section right here, say, and that is some value x. Okay, as we move up in y, this value of x changes. For example, right here, the width, which is a function of y, equals 0. I'm sorry, the width at 0 equals 0. The width at 6 equals 0. And the width at 3, which would be this point right here, has to equal the radius. So it equals 3. And I need it to vary from here to here, and so I have to develop an expression for x as it varies along the edge. That will give me the width if I multiply it by 2. I said this is a little more difficult than the others. Okay, how am I going to find out what that width is? I need to find a value for x of y. In other words, to find the radius of that circle as I move from y equals 0 to y equals 6. What this really is a circle with a center at 0, 3. So I can write the equation for the circle at 0, 3. And you can see where you put your coordinate system makes a big difference here. Okay, since h is 0 and y is 3, here's my expression for that circle around the outside edge of that drum. Solving for x, I get x equals square root of 9 minus y minus 3 squared. I'm going to put this into the equation here. So gamma, these first two terms are the pressure. Pressure equals gamma times depth. This is the width as a function of y, and then the dy gives me the height of each little section, infinitesimally small height. And that's why this is a definite integral. I integrate from the bottom of the drum to the top of the drum in y, from y equals 0 to y equals 6. That integral gives me my entire force on the drum. So here's a summary of the process for computing forces on vertical plates that are submerged in some fluid. To solve the problem, we divide the problem into little linear problems. The vertical plate is divided into horizontal strips. The height of each strip is delta y, or it turns out to be dy in the definite integral. The width of the strip is some function of y, some function of the depth. To find delta y can be the hardest part of the problem. Now we need the area of each strip, which is that width times the height. Then the force, which is pressure times area, is pressure times width times height. For the approximation force is the sum of all the little forces, but in the limit this becomes a definite integral. I'm not specifying the limits of integration because that depends on the exact shape and the coordinate system that you put in the sketch, which you've done before you've done anything. But it's going to be pressure, which varies with depth, the width of the object, which varies with depth, times dy integrated over the entire object.